Buenas tardes nuevamente. Vamos a retomar, ¿no?, la segunda clase de este minicurso sobre fundamentos de neutrinos que comenzamos ayer. Justamente quien nos está brindando este minicurso es el doctor Hélio Motta del Centro Brasileiro de Pesquisas Físicas. Okay, esperamos unos segundos hasta que cargue la pantalla del doctor Motta.
It should be there already.
Okay, we're ready when you are.
Okay. So I continue what I started yesterday. And let me go to my vertical views. No, not this one. Wait a minute. Okay, this is what we started yesterday. Let me see where I stopped. Yes, that's where I stopped yesterday. Okay, I showed briefly. I don't expect to be. I don't want to go into details, but just want to show you how it was possible to know if it was a muon or electron. Remember, just to remember things. Electron, muon, and tau, they are pretty much the same. They look a lot like each other, but the muon is much heavier than the electron, and the tau is even much, much heavier. Apart from that, they are pretty much the same. And each one of them has a partner with no charge. That's a neutrino. So the electron has a partner neutrino that's called electron neutrino. The muon has a partner that's a muon neutrino. The tau has a partner that's a tau neutrino. They are different. They are not the same. Okay, because we know that the muon neutrino produces always a muon. An electron neutrino produces always electron. So they come together. And why? Someone asked why. Well, I don't know why. That's how the universe works. Okay, so in this, there was the question because it was found out that neutrinos coming from the sun. The neutrinos we could see here on Earth, we could see only about 1/3 of the neutrinos that were supposed to come, and the idea was that there was an oscillation. So as they travel, a mu neutrino turns into a electron neutrino, a tau neutrino, and so on. So if you give them enough time, enough distance to travel, we will observe this phenomenon if it really exists. So some experiments were designed for that. So I talked about this Kamiokande, how it works. That's it. Well, but so neutrinos do not come only from the sun, as you said. There is also cosmic ray, atmospheric neutrinos. What happens is that a cosmic ray, that we see here, I need some here. Okay. Here you have a cosmic ray. Okay. The cosmic ray hits when it gets to the atmosphere. Cosmic ray comes from the universe, from wherever it's coming from, hits the atmosphere. So this interaction, they have very high energies, very high speed. They produce lots of things. Lots of things are produced. And here we just show example what could happen. And if you pay attention here, some of these productions here, down here, see? Okay. At the end of all these productions, neutrinos come. And here you see that they are electron neutrinos. This one here is an electron neutrino. Okay. And then we have muon neutrinos. Okay. They're also anti-muon, the antimatter of the neutrinos. So here on Earth, from the sun, we are expecting only electron neutrinos. But atmospheric neutrinos come in at least two flavors, electron and muon neutrino. So, based on this, what you see here, if you measure the flux of muon neutrinos and compare to the flux of electron neutrinos, we should see two. So we have two, for each interaction of those kind, produces two muon neutrinos and the only one electron neutrino. So that's what we should see. Okay? Now, remember that I said that it takes time. So the neutrinos have to travel a long distance so we can observe this oscillation. So when you work with the reactors here on Earth, the distance is too short. It doesn't happen. So the one coming from the sun travels a long distance. But what are they doing here? They are getting neutrinos from atmosphere. The atmosphere has about, let's say, 50 kilometers to 100 kilometers, maybe, okay? Just about 100 kilometers. So these neutrinos are traveling a few hundred kilometers to Earth. So how do we get them to travel a much, much longer distance? Okay, that's the trick. Here we have our planet, Earth. Okay? And here, let me change now color. Here I set my experiment. Uh-oh. Here I have my detector. Okay? Of course, I am exaggerating. Okay? And then come the cosmic rays. Uh-oh. And the cosmic ray comes here. I hate when these things happen.
Relax, be cool.
Okay. The cosmic ray. Okay. Then produce neutrinos. And then I get neutrinos here. Blah, blah, blah. Okay. Fine. So to reach my detector, they travel about, say, 100 kilometers. However, and that's the trick, cosmic rays from everywhere on the universe. So you have also cosmic rays coming here. Okay? It means that we also have neutrinos. Here this way. Okay? And neutrinos, remember, they go through matter, no problem. So neutrinos here will come and also hit our detector. However, the neutrinos at the top, they travel about, say, 100 kilometers, just giving a number. But neutrinos coming from the bottom, they travel the 100 kilometers from the atmosphere, and plus they have to cross the planet. So it's 10,000 kilometers or so. So they travel a much longer distance than the other ones. And the detector is able to see both of them. Okay? So if you compare here, the flux of neutrinos coming from up to the flux of neutrinos coming from down, talking only about the mu neutrinos, this should be equal to 1. If there is no oscillation, okay? The same thing. Should be able to count as many neutrinos coming from the top as coming from down. So they run that experiment, and surprise, surprise, that didn't happen. We could see more coming from up than coming from down. So it was always a good indication that neutrinos coming from down, they were traveling a much longer distance. And then they were oscillations. So they were able to observe this oscillation phenomenon, always from neutrinos coming from atmosphere, not just from the sun. So this was a very good indication that, in fact, oscillation was happening. But they observed that on the sun, observed now on Earth. So then this was the super Kamiokant. Now, then another experiment was set, because you still have to find, if there's only 1/3 of neutrinos coming from the sun, whatever, we must find the other 2/3 to make sure that they are really there. Okay? This other experiment is called the Sudbury Neutrino Observatory, SNO for short. It was set in Canada. Here to the right, you have a sign of the, see here? There is someone there. He's a real person, a normal-sized man. Okay, and here's the detector. Remember, neutrino detectors are usually big because you need lots of mass to be able to see some of the very few interactions of neutrinos. So here's there's another one here. And this is underground. It's usually underground. So you use the mountain, all the rock, to shield the detector for everything in a way that only neutrinos will pass and hit the detector. So they built this new detector, SNO. It's about 1,000 tons of heavy water. It's lots of water in there. Okay, it's big, 12-meter diameter. And as usual, it's always the same. It's surrounded by photomultipliers as there. And what happens with this detector? It was built in such a way that it was able to see, to get interaction and see all flavor of neutrinos. So it was able to get to see electron neutrinos, to see muon neutrinos, and to see tau neutrinos. Okay? And so they did. And so they could compare the flow of electron neutrinos at the top compared to the flow of all three kinds of neutrinos. And see, guess what? They found 0.34 or 34%. So they found 1/3. So from all neutrinos that were coming, 1/3 were neutrinos from the sun, and the other were there. So this result, this percentage here, was in perfect agreement with the Dave's experiments, that one that first observed neutrinos from the sun, and found that only 1/3 of electron neutrinos. Where are the other 2/3? They are here. They found that, in fact, there were 34% of the neutrinos coming from the sun were electron, but there were the other 70% of the neutrinos were muon neutrinos and tau neutrinos, and the sun does not produce muon neutrinos. The sun does not produce tau neutrinos, according to the model. Yeah. So, let me see. So, what happens? In fact, neutrinos coming from the sun are oscillating. So they were able, together with the other one, to show that neutrinos were oscillating. Okay, and when they measured the total flux, they found the total flux was about 5, 4.94, and the theory was predicting 5. So it's the same thing. If you compare the error, so they finally were sure. Okay, no matter whether you like it or not, neutrinos do oscillate, and they have to do that. Okay? So just to have an idea, I'm not going to get in detail, but show how it works. Remember that when I talked about the other one here, I showed that we have these rings on the wall. Okay? That's pretty much the same here. But here, the detector here is a sphere. Okay? It's a globe. So what happens, pretty much the same thing. When the neutrino interacts there in the globe, even today, I'm going to talk a little bit how that happens. Produce light because of the charged particle that's produced, electron, muon, whatever, interacts. And they also have rings, but the rings now are distributed in this globe. And they can also reconstruct. Reconstruct means the following. We really do not see what happens. What we have is signals, electronic signals that come from all the photomultipliers. Using those signals, of course, we have a software for it. Using all those, we have to try to reconstruct, to rebuild what happened. What happened that produced this? This is reconstructing the event and know exactly what happened. So that's pretty much like they do. And this kind of experiment, they were able to see interaction from muon, tau, and electron neutrino. This was a big achievement. Okay, people got a Nobel Prize for that, for making sure that neutrino oscillated. The two guys, the guys from Canada, and the guy from Japan. Super Kamiokando was in Japan, this was in Canada. They got a Nobel Prize for this. Okay, and so what? Do neutrinos exist? That was a doubt at the very beginning. And the answer to this is yes, they exist. It was proved that they exist. They were able to observe neutrinos. Okay, they exist, fine. What they are for. Do they have flavors? Well, yes, they have flavors. We have at least 3 flavors of neutrinos. That's the electron neutrinos associated with the electron, the muon neutrino with the muon, and the tau neutrino with the tau. Okay. There is a possibility there are more neutrinos, but I'm not going to talk about this now. Okay? There are at least 3 flavors of neutrinos. They oscillate. Do they oscillate? Oh, yes, they oscillate. Now we are sure about they oscillate. They have mass. Okay, if you remember when they're talking about this oscillation stuff, we got to that expression that showed the probability of a neutrino of one kind to turn into a neutrino of another kind. This would not happen if that angle that measured the shift were 0. Okay, and also not happen if that difference of the square mass difference, the difference between the square of the mass of neutrinos, were 0. Since we know that oscillate, then that angle is not 0, they had to be measured, and the mass difference would not be 0, means that neutrinos have a mass. What's the mass? If the mass is too small, what's the mass? Well, we don't know. We still don't know the mass. Some experiments were able to measure that mass difference. Because remember, if we are able to measure that probability, that expression I showed is a mathematical expression. It shows the probability of something happens. So the probability of oscillation. So if you go there and measure the oscillation, we can do the other way around. We have the measurement of the oscillation, then you put that value in the formula, and you get the angle, and you get the mass difference. So this was done. So they know there is a mass difference, but they do not know each one of the mass yet. Another point is the following. Neutrinos have no charge, no mass, almost no mass now. Okay, but are neutrinos really different? A neutrino is different from the antiparticle, the antineutrino? Well, there are some questions about that. People are not sure because there is not enough measurement yet to be sure that a neutrino and the antineutrino are really two different particles, or if they are the same particle, just manifesting themselves in another way. We don't know. Oh, sorry. And how neutrinos interact? So I told the neutrinos do not interact much. They go through a block of lead without interact. We need at least a 20 light year block of lead for a neutrino to interact, to produce something that we can observe. That's how it happens. When someone gets a ball, if you're playing soccer or whatever, and the ball hits you, you feel the ball. Somehow that ball interacted with you, and you could feel that it happened. So for a neutrino to interact means what? How does it happen? How the neutrino rarely, very rarely, but sometimes happens. How it happens? How this interaction happens? We do not know that very well. I'm talking a little bit about this even today. But then we must investigate all this. All this must be investigated. Neutrinos have to know how neutrinos work. How do we investigate? So they have a very small cross-section that makes it very difficult to have an experiment. You saw the detectors I showed there are huge. They are really big. Okay? So we need big detectors. And we need a very intense flux. Or better, we need both. A very intense flux and the big detectors. That's complicated to produce. They have no electric charge. So what happens when you have a detector like that? What you really observe is something electrical, electromagnetic. Okay? So basically, we are able to observe particles that have a charge, like an electron, a proton. Okay? That's what we need. Neutrinos have no electric charge. So they go through the detector, nothing happens. So it makes things very complicated. What you really observe is only when it interacts. What are the sources that you use for that? Well, I mentioned you have cosmic rays that are produced by the universe, nature. You have the reactors that you build, and now we have accelerators. Let's talk a little bit. I'm not going to get details, just to show you an idea of what I have. How we do experiments with reactors? Well, the reactors are there. They produce neutrinos. In fact, they produce antineutrinos, but it doesn't matter here. And they have a very intense flux. Okay? So the flux is very intense. In principle, you know what's the flux because we built the detectors. The reactor is built, so we know what we're building. You know the power of that reactor, so we have a very good idea of the intensity. And so we can build this even small or medium-sized detectors, or a few tons. Let's put them close to the reactor, and then we see what happens. But you don't have control of the flux. Okay, the reactor produces a very intense flux of neutrinos that goes everywhere in all directions, not only to our detector. Okay, so this is a picture of a detector experiment that's in Daya Bay, that's in China. Okay, what they do? They use 8 antineutrino detectors. Remember, this is a reactor. So, and what they do, they have a big site there in China with several reactors. They have 6 nuclear reactors. And so they use these 8 detectors around these 6 nuclear reactors, about 2 kilometers around. Okay, this is just a view of the detectors. Okay, to the right, you see the detector. So each detector, each one of those 8 detectors, has 20 tons of a liquid scintillator. What's a scintillator? I told you that when you observe a particle charge, what you use is a scintillator. It's a material that when an electric charge, like an electron, for instance, goes to that material, it produces light. It scintillates, produces light. And the light, that's what you observe using the photons multiplier. Okay, so you have the system. It's basically a tank, a reservoir full of water or of a scintillator or whatever. When the particle goes through that material, it produces light. And then the photon multiplier is able to see that light. And then we get the signal from the photon multiplier. And if you are smart enough, you see the figure to the left, we are able to reconstruct from all that signal, like you had up there with the rings, reconstruct what happened. So that's what they have 8 detectors like the one here. Yeah. Okay. And with this experiment, they were able to measure, here see, they were able to measure the mass difference between neutrinos, a very small value. Okay. Now, what we really like to do is to use a neutrino beam. We have here, how do we produce a neutrino beam? Okay. If you have a particle with charge, like an electron or a proton, it's pretty much easy. Why it's easy? Because you have an electron has an electric charge. If you just have a magnetic electric field with a potential difference, some volts, then the electron will be accelerated. Remember, the force will be a charge times the electric field. So if you have an electric field, and that electric field will have a charged particle like an electron, it will be accelerated. Force, with the force it will move. So you accelerate, and you have a beam. If you have many electrons, you have many electrons accelerated at high speed, give energy. So you can do the same if you have protons. Protons have a charge, but how to do with neutrinos? Neutrinos do not have electric charge. So nothing happens. I don't have a way to produce and accelerate. So we have a short video that illustrated how it's done. I'm asking Professor Castromonte to show the video. Do I have to stop sharing my screen for that?
Okay.
I will stop sharing my screen.
Which of the video do you want me to share?
Very.
Okay.
Which ones you have? How do you stop sharing
both of them. There is one called Como fazer feixe de neutrinos. Is that the one?
Wait. Sorry. Wait a minute. Let me go there. Yes, that one. Let me stop sharing my screen.
I'm going to share my screen.
Sorry. Okay. Is
okay,
there?
Just a minute.
Okay. Now can I start sharing my screen again?
Yes, please, go ahead.
Okay, let me go back there. So, so what the movie showed us, the cartoon showed us, basically what you have protons coming, that's what they show. Protons are charged particles, right? It's, as I said, it's easy to accelerate. And you make the protons collide with a target. This is a target, okay? And when interact with target, many things happen. Protons interact a lot and produce lots of things. Many particles come from that collision. Some of those particles are what we call pions and kaons. Pions usually represented by the pi, and the kaons. I'm going to talk about that later, but pions and kaons, remember that I said the particles, they have a tendency to go down, to decay, to things that's lighter. And that happens with the pion, it happens with the kaon. And in the process of decay, remember there at the very beginning when I said about the tritium experiment that gave origin to all this blah, 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 blah about neutrinos, because they, in the decay process, when they go into a lower level, a neutrino was produced, the same happened here. This pion going down to a lighter particle that we're going to see later, or they count, they produce a neutrino. So that's the trick, okay? We use the proton produces pions again. Pions are charged particles. Since they have electric charge, we can do a lot with them. We can use a magnetic field or an electromagnetic field to control them. So we end up having a beam, a very well collimated beam of pions and kaons. So when they decay, they produce neutrinos. So then what you do? We wait for them to go. At some point they decay. Takes some time. So that's why we have this long distance. This is a decay area. Okay? A decay area. So the pion and the counts go and they decay. Once they decay, we have neutrinos. Huh? Have neutrinos. But we have other things. Remember that the proton here interact to produce lots of things, not just the pions and counts. So, but you just want a beam of neutrino. What you do, you just have here rock. Okay? Rock. Because you do that usually underground, and they use a rock, a mountain, whatever. And everything stops there. It stops everything except neutrinos. Remember, neutrinos go through everything. So after this rock, we end up with neutrinos. Okay, here I have neutrinos and the other thing. So we end up having a beam of neutrino. So up to this point here, we don't have control anymore, but we have control here. Remember, see, since we have control on this proton here, we have control on the proton, and you also can control the pions account. We can select the energy that we want. So we can have protons with more energy, we can have pions with more energy, then we can control what will be the energy of the neutrinos. And if we, depending on how many protons we make collide, we have more neutrinos. So we can control the intensity of the neutrino beam, meaning intensity means how many neutrinos per second per square meter we have. And we can control the energy of the neutrinos. We have full control. We don't have control neutrinos coming from the sun. We don't have control neutrinos coming from the atmosphere. We don't have control of this from a nuclear reactor, but here we have control. So this is very important for the experiments. We have full control. We know, okay, we know we have as many neutrinos as 1 million, 10 million, 100 million, whatever. We know how many we have. And we know the energy of the neutrinos. What's very, very good to start with. Okay? How this in the real life? Well, that's pretty much how it really looks in real life. Okay? It's the labs. If you go to a lab like Fermilab or CERN, and I hope that at least some of you one day will go to one of those labs, and they do not really look like the ones you see in the movies. Okay? There is one movie that was very popular from the same guy from the Da Vinci Code. I don't remember the name, but it happens as, what's the name of the movie? Remember the one that talks about CERN? Anyway, and they showed the experiment, the supposed experiment at CERN. That's one of the big labs. And I started laughing when I saw it, because it doesn't look a lot, okay? Labs are not as nice as they show in the movie. Here you see, that's what the protons from accelerator come from, the protons from accelerator, okay? There is some target there, and this is the long heat. You have two guys here, see? Two guys. All this is underground, okay? All this is underground. So the area that you expect you allow the neutrinos, the pions to decay to produce neutrinos is about 675 meters, so about almost 700 meters. So a very, very long pipe, empty. There is some level of vacuum there. So the pions, the ions, they go and they decay. At the end, you have only neutrinos. And then at the top there, after all this, you have rock, just a rock, earth. This is about 100 meters underground. And then finally, you have only detector, only neutrinos, and neutrinos arrive here. And that's this big thing here. Big. This is a detector. There is someone here. See? A man here. There is someone there working there. And so this is a big detector. So that's how produced. Here we see a view. Here is the main building of the lab. This is at Fermi lab. Okay? And that's how it happens. Is everything is underground. Everything is underground. And here we have our detector. This one. That's about 100 meters underground. Okay? And here shows what happened. The protons interacting. Okay? We have the target. Here you have the pions and the counts or whatever. And they travel for some time, so they decay, and they end up only with neutrinos. Okay? Mu neutrinos. That's what you produce there, mu neutrinos. Okay? So what to do that? Well, we have some experiments. I'm not going to go into details just to show you. So this is the experiment that was called MINOS. Yeah? Remember, we mentioned that neutrinos oscillate. Okay? So they change as they travel. So how can we measure the oscillation parameters? Okay, how can we do that? The way to do that is the following. We have to measure the neutrinos to make experiments in two different distances. You have a detector at one point, and then away from the detector, you have a second detector. So we measure the neutrinos in two different locations, and they are separated by a distance that's long enough so oscillation may happen. That's what we have here. So there are two detectors indeed. Two detectors. One is very close to the neutrino source, so very close to the accelerator itself. And the other one is almost 800 kilometers away. It's a very long distance, okay? Very long distance. And they work with neutrinos and antineutrinos. So the near one, the detector that's close to the source, is big, about 1,000 tons. They are very heavy. They need lots of material, so some neutrinos will interact. It's 100 meters underground, and they have calorimeters. So what are calorimeters? Maybe you saw this in physics. This is a device that the name suggests it basically measures energy. So how do you know the energy of something? Well, the way to measure the energy is transferring that energy to another subject, like for a thermometer. Right? You can measure the energy, have a thermometer in the water, you measure the temperature, you see how much energy was transferred. That's pretty much what they do. They don't measure the temperature, of course, but they get that particle. It transfers all the kinetic energy of the particle to what we call a calorimeter, and then we measure that the energy that was there. See, the energy here came from the particle, so the particle had this energy. That's easy, how you do it. And then you have the second detector. That's much bigger, okay? And it's deeper. It's about 700 meters underground. And the distance is about 800 kilometers away. They use their old mine that has not been used as a mine anymore. So that's the second one. It's much bigger. One reason why it's much bigger is because this beam of neutrino, here we have a design here. Okay, here you have the lab on that we produce. So the near detector is here. So near detector, ND, and the far detector there. So almost 800 kilometers. So contrary to what some people say nowadays, the Earth is not flat. Okay, so the neutrino beam goes through Earth and hits the second detector here. Okay, and this is underground, about 1,000 meters underground, much bigger. And it has to be bigger also because the neutrino flux beam is not very collimated, so it goes pretty much like that. So if at the beginning we have a detector here, if you have a detector the same size away from there, most of the neutrinos will miss the detector. So you have a much bigger detector because the intensity of the flow here is different. Unfortunately, you cannot have a beam of neutrinos that's very well collimated. So the second detector far away, very far away, it has to be much, much bigger. Okay? See the guy here? Okay? Now, this experiment here was designed to measure oscillation, to observe how neutrinos oscillate. Another experiment, the Minerva experiment, where Professor Castro Monte was also a member of the Minerva experiment, is another experiment that is not designed, was not designed to measure the oscillation. But say, I mentioned before that you must understand how neutrino interacts. Okay, so we must know what's the cross section. We know that it's hard for neutrino to interact, and the probability of interacting, we call it cross section, but we must measure it. So a neutrino experiment basically was designed for that, to measure the neutrino cross section, how neutrino is interacting with matter. So it's also a big detector. We see here the detector here, about 180 tons, so they're heavy. No? And there are several layers of scintillator. Remember what's a scintillator? It's a material, when the particle goes to the scintillator, produces light. And then, guess what? You have photomultipliers here. Photomultipliers. All these are photomultipliers. Photomultiplier. So the light goes to photomultiplier, and then we have electric signal, and then we have to make a reconstruction anyway. Okay? And I was able to make a very precise cross-section measurement for neutrinos and for antineutrinos. So this is just a scheme of the detector. I'm not going into detail, but the neutrinos are coming here. They're coming here. And then here when they find the detector has steel, has carbon, has lots of material. Eventually, something is going to happen here, produce a signal. The signal produces light, and the forms get light. And so we have this. Not much detail, so we don't have time for that. I'm going to skip these things here because to describe, because maybe later I talk about this show how things really look like when you see, but this is not the moment for that. Now, we are now going to talk a little bit. Another experiment is called Dune. Dune is an experiment that is being prepared, and is a huge experiment. Much, much bigger than the Minos that I showed, much, much bigger than the Minerva. And this big experiment is designed to make very precise measurement of several neutrino features. People from Peru, from Uni, also part of this experiment. Professor Castro is one of the members. And there have been a long collaborations. The Dune stands for Deep Underground Neutrino Experiment, and it means that it's really a big thing. It's underground, really well underground. And let's see how it happens. How it will. I will have another video that helps to clarify this. I'm gonna again cancel, stop to share my screen, and ask Professor Castellman to show the other video. Can you hear me? Hello?
Hélio?
Hello, can you hear me?
Yes.
Can you pass? Can you show the other video?
Yeah, sure. Just a minute. Okay.
This is Fermilab, a Department of Energy National Laboratory near Chicago. It's the starting place for the deep underground neutrino experiment, Dune, powered by the Long Baseline Neutrino Facility, LBNF. The experiment begins with Fermilab's accelerator complex, which moves protons close to the speed of light. It's all part of an effort by more than 1,000 scientists from around the world to figure out how tiny particles called neutrinos work and what role they play in the evolution of our universe. Neutrinos are the most abundant matter particles in the cosmos, but very hard to catch. Trillions stream through you every second without leaving a trace. At LBNF, the beam of protons will smash into a target, creating the most intense beam of neutrinos in the world. Scientists will collect data to measure properties of neutrinos close to the source and again far away. Neutrinos change as they travel, so scientists are sending them straight through 1,300 kilometers of rock toward the Dune detectors at the Sanford Underground Research Facility in South Dakota. The detectors can also look for the birth of neutron stars and black holes by catching neutrinos from exploding stars. The 1.5 kilometer deep detectors will be filled with 70,000 tons of liquid argon, making them the largest neutrino detectors in the world. As neutrinos interact with the cold liquid, they create a shower of other particles and light. Those particle tracks are then picked up by electronics and transmitted as data to the surface. The information will be analyzed by scientists at collaborating institutions in countries around the world. They'll use this data to solve unanswered questions about neutrinos, and maybe even figure out why matter exists. Things like planets, stars, and even you.
Okay. May I start sharing my screen again?
Yes, please.
So, Professor Castro is recording this presentation, so you can see this video later. And that maybe there is a version in Spanish, or at least with subtitles in Spanish that we can use. So, but this is the idea. If you saw, as you saw there, it was, again, the same thing. They start with protons that accelerate to very close to the speed of light, as I said, and then collide with the target, producing lots of things in the end with a very, very intense neutrino beam, very, very intense, and then produce, and here's a view of the lab. Okay, this is the main building, the building of the lab. Okay, this construction here. Okay, and then that's how things happen. So they start here with the protons, they accelerate, and after this, they have to accelerate. The way they accelerate a proton is, if this is a little bit old, this thing here does not no longer exist, but they send a proton to a ring, okay, in the way that every time it goes around the ring and it gets more energy, accelerate, and then again, and again, and again, and again, and again, and again, until the proton reaches the energy that we need, so the speed. Once that happens, they make the proton collide with the target and produce everything, and then end up with a beam of neutrinos. And this beam of neutrinos then is sent to a long distance. In case for the minus, see, this is the difference. It's a very long distance here. The minus that I mentioned before. And here we have another one, much longer distance. Basically, it's going to be with this Dune experiment. They start with, again, there will be two detectors there, okay? So what about the Dune detectors? Well, they mentioned that they are very, very big. Just to have an idea, they are basically 4 tanks. Each of them has 10,000 tons of liquid argon. Argon is one of those noble guys. Liquid argon. The way you have argon, that's naturally a gas, liquid, is in a cryostat. It's basically a container that you keep in very, very low temperature. So you have all that gas, that argon, in liquid. And they are very, very big. So to have an idea, there will be 4 of them. Each one is about 15 meters by 14 by 64. So it's a very, very long, if you imagine this is a container, like a cylinder, it's 62 meter long and 15 and 14, like a cylinder that's very big. And we need 4 of them. Of course, they are not going to build 4 at the same time, do one at a time. To have an idea how big they are, here's the Maracanã Stadium. Probably all heard about the Maracanã Stadium. But any other soccer, the big soccer, they will do it. And here you have the field. Okay, here's the soccer field. So if you try to put all the Dune detectors in this Maracanã Stadium, well, they will not fit well. They are bigger than a soccer field that has about 100 meters, so it will be much more than that. Remember that, as you mentioned, they have 62. So if you have 4, the 4 are here. In fact, they will be here. 1, 2. Say 1, 2, 3, and 4. Okay? They don't fit. It will be 120 meters, more than the soccer field anyway. And the height, they are 14, so this is about 14. It's a very, very big thing. And they are all underground, about 1,000 meters underground. They have to take an elevator to go all the way down. Okay? Very big thing. So, how is it? They have a very intense, it's a very intense neutrino or antineutrino being. How it changed from neutrino to antineutrino? I want to see that later, but you saw that pions, when they decay to something like, they produce neutrinos. That was the pion. If you have the antipion, it's a pi plus, positive charge. The same as a pion, but the charge is opposite. Then it produces the antineutrino, okay? And since you produce that, and since they have electric charge, we can select at the very beginning if we want a pi minus or a pi plus. And then we have a beam of a neutrino or the antineutrino. So we can do that. So basically what happens here, okay, you see the neutrinos go, and you see the beam here starts pretty much narrow, but here is much wider, okay? Much wider. So that means the detector here has to be much, much bigger. Okay? There's a huge detector about, this distance here is about 800 miles. Americans still have this many of miles, about 1,300 kilometers away from the source, about 1,000 meters underground. Basically, doing science, I'm going to talk just a little about it. What they plan to do with this. Okay, remember I mentioned at the very beginning that you have observed lots of matter in the universe, not much antimatter. So something happened in the beginning. If our idea Big Bang is correct, we should have the same amount for both of them, and they would annihilate, there will be nothing there. The universe exists to have lots of matter around, so this difference may be what we call a CP violation. CP violation, to make it simpler, we mean that the physics for matter and this physics for antimatter are not exactly the same. No, they are different. There's some difference. And this difference may explain why, at the end, matter exists more than antimatter. Well, they have to study CP evaluation. Why they do that with neutrino? Because neutrino is the hope now that it happens. One of the hopes is neutrino. And basically, what you have to do is to observe, to make measurements for neutrinos and the same measure for antineutrino. If the physics is the same, the results should be the same. We should be able to observe the same physics. Remember, we have the expression for the probability for the oscillation. So if the physics is the same, the probability of oscillation, the oscillation of neutrinos and the oscillation of antineutrinos will be the same. We don't know yet because we don't have enough measurement. But there is a hope that there is enough difference to explain what we have. Another point is that we know that the neutrinos have mass. And experiments have measured the square, the difference. They have measured the difference m to 1 minus m to a square. This have been measured. Okay? But then also know that we have at least 3 neutrinos. However, there are 2 possibilities. we know that two of them, the mass is very close, the other one is much bigger. However, we have two possibilities. The two neutrinos whose mass, very small, are very close to each other, are down here, and the other one has a much higher mass. Or one is the other way around. The two have a mass that's much bigger than the other one. One we call the inverse, and the other is the normal. We don't know yet which one is true, which one happens. We have to measure. And this is important because this changes, affects the theory and how things are studied. So we have to determine the mass hierarchy. And we have to make a precise measurement of the oscillation parameter exactly to understand how things happens and if neutrinos and antineutrinos are different. Another possibility, another thing that the theoreticians have been discussing is if a proton decay. Well, we know the proton, let's say in the atom, and so far as we know, and a proton is a stable particle. Means that a proton will be a proton forever. Leave the proton there and look 1,000 years from now, 1 million years from now, 1 billion years from now, and the proton is there stable. However, there are some theories that have developed that it would imply that the proton may decay. So a proton may go down to a lighter particle. And way it shows this one. And guess again, a neutrino is there. Okay, neutrino is there. So if the theory is right and nobody knows it's right, and some people believe it's totally wrong, a proton may decay. It may go into a kaon. A kaon is a much lighter particle than the proton, and so as a neutrino. The problem is, if that happens, there is a violation of several things that you believe sacred. So it's very important to find out if a proton can decay or not. Okay, a way to do that is observe a proton, but you need lots of protons to observe. So far, at the beginning, I think that the minimum would be 10 to 31 years or so. Because that's how we do. We observe, and if you don't see any decay of the proton or whatever, you say, okay, I know that if it decays, it takes longer than 10 to 31 years. Okay, how we do that? We need lots of protons to observe. And this huge detector that we have there, remember, this much bigger than the soccer field, they have zillions and zillions and zillions and zillions of protons. So if a proton decay, there is a chance of observing a decay of a proton there. But for that, remember, it's a neutrino experiment. We have also to detect the neutrino and behave. So this will be something very important to do. And another thing is supernova. Why supernova? Supernovas, we don't know when a supernova will happen, okay? But supernova produce lots of neutrinos. I mentioned that at some point. Most of the energy of a supernova comes as neutrino. So when a supernova happens, we don't know when it's going to happen, and it produces a burst of neutrinos, and the detector like Dune will be able to detect that burst and make lots of measurements about it. A few months ago, about 1 year ago, so people got very excited because if you look at the sky, and you have heard the star named Betelgeuse, okay? Betelgeuse is a star that's visible, and the astronomers and the cosmologists know that the star is going towards to become a supernova. They don't know when, but it could happen at any moment. And some measurements for some experiments suggested that it was about to really explode as a supernova. So people got very excited, started observing, but they found out that the measurements were wrong. But at any moment, there will be a supernova, and a detector like that will be very good to measure, to get very good measurement from what happens in the supernova. So what's the strategy for Dune? Okay. First of all, a detector at Fermilab, so close to the source, we measure the neutrino beam without oscillation. Why without oscillation? Because it's very close to the source, where the neutrinos are produced. And since they are produced, they don't have enough time to oscillate. So we measure everything there. And then we have the other detector at surface. Surface is the one that's over 1,000 kilometers away. We have the second detector. And we measure the same thing. But in that case, we are going to measure the spectrum that already oscillates. So at the beginning, we have only a beam of a neutrino, mu neutrinos, like here. Okay, and then 1,000 kilometers away, we measure, and you should be able to see both neutrinos. These electron neutrinos are resulting from the oscillation of the mu neutrino. So since we can do very precise measurement of both things, we can have very good information about the process of oscillation. That's for neutrinos. And they will repeat the same for antineutrinos. Do exactly the same thing. Okay, but in the case we use this bar here, shows that's antineutrino. But it repeats the same thing. And note, so we're using the same detector, the same technology, the same machine. So, and then we can make a very good comparison between neutrinos and antineutrinos. It seems to be high precision. We should be able to see difference, and then see if neutrinos and antineutrinos behave in a different way. And if that's the case, we could be able to see if there is really a difference that could explain the difference, the presence of matter in the universe. And finally, the supernova. Okay? The collapse of supernova nucleus produces a very intense pulse of, it's a pulse of neutrinos. It doesn't last years. It's a pulse of neutrinos, very intense. Then you can observe that in our detector. Also, a neutron star produces also a bunch of neutrinos. Neutrinos are everywhere. Okay? And then there is a possibility to also see the formation of a black hole, because also neutrinos are everywhere. Yeah? So to finish this part here, you must pay attention to what? Well, neutrino physics has an exciting history. Okay, everything dealing with neutrino brings a surprise, full surprise. And neutrinos oscillate, what's also a big thing that happens. They have a very small, but not zero, mass. And this mass has yet to be measured, has not been measured. There is a possibility of DCP violation. And that maybe can explain that matter prevails in the universe. Okay, what happens if that's not true? Well, then physicists have a problem. They have to find another explanation for why there is more matter than antimatter. Maybe the idea of the Big Bang is wrong, not like that. So it's very important to find if this CP violation really exists in neutrino or not. A no result is also a good, very good result. We're not saying that it happened. We are pretty much sure that there is some violation of this principle. Not that the universe is crazy, just because we believe that there is this symmetry, called the symmetry. We are crazy about symmetry, but maybe that's not how the universe works. Okay. What you know about neutrinos, the problem is that it does not fit into the theory we have now. It doesn't fit. The theory was developed, and in the development, the theory, neutrinos were there, but they were supposed to have no mass. Now we know they have a mass, so they oscillate. That makes a big mess. It's not very simple. Just say, okay, let's just add this to the theory, because the theory that explains the mass of each particle has a mass. Okay, electron, proton, and so on. The theory explains the mass of all particles, but it would not explain the mass of the neutrino for reasons that we see later. Another point is that it may sound strange, but we don't know exactly if the neutrino and the antineutrino are really different from each other. It's something we have to see. Maybe there is a difference between both of them. For instance, a particle like a pion, apply minus and apply plus are very different. They have different charges, but neutrinos have no charge, so this cannot be really different. Maybe neutrino and the antineutrino are pretty much the same particle that just changed from one state to the other state. We don't know. Now, we know that we have three neutrinos, right? The neutrinos from the electron, the neutrino from the moon, and the neutrino from the tau. Maybe there are more neutrinos. I'm going to talk about this later, maybe today or tomorrow. But there is a possibility that there is another kind of neutrino, maybe a stereo neutrino. That's a neutrino that's very different. This has to be measured. And there are new experiments like Dune prepared for that. Okay? So I finished this first part, but I'm not finished for today. We still have time today. I still have 30 minutes to go. So Okay, this is for the brief introduction. I think I showed a lot for just one day. So what I want to show now is, I think this one here, let me see. Okay. Any question about this thing that I talked about? I try to give you more detail now about the neutrinos. Okay. Explain something more. That's why I called it the introduction to neutrinos. Well, the year, not the year. Well, it's 2000, we know the year, right? 2021. So I'm talking about neutrinos, but we cannot just take neutrinos away from the rest of the universe, the other particles, because as we see, they come together with electrons. They come together with muons. So we have to understand a little bit what happens. So we have to understand what we call the standard model. The name basically of the theory that we have today that is supposed to describe particles and how interact, and we're supposed to describe neutrinos. We know already that it does not do well for neutrinos, but anyway, that's what we have now. Okay, so basically it deals with the fundamental constituents of the universe, the matter. So those are what we call elementary particles. An elementary particle is a particle that's fundamental. It does not have a structure. An atom is not a fundamental particle because an atom has electrons, protons, and neutrons. So it's not fundamental. Okay, the nucleus of an atom is not a fundamental because it has protons and neutrons in there. An electron is a fundamental particle because there is nothing. The electron is not made of other particles, so it's a fundamental particle. Okay, and the proton and the neutron inside of the nucleus, what belief is years ago that they were fundamental particles, elementary particles, but they are not, because now we know that protons and neutrons have a constituent that we call quarks. Talk a little bit about it later. So they are not fundamental. But electrons, as far as we know, are fundamental. Neutrinos are fundamental. As far as we know, neutrinos don't have anything that make neutrinos. Neutrinos are by themselves. Then we have atoms. What are atoms? Atoms are basically a bound state of electrons, as I mentioned, protons and neutrons. You have get electrons, protons, put them together, and you have an atom. An atom of helium, uranium, gold, whatever. So that's all they do. Now, electrons, that's very important. How do electrons are bound to nucleus? What keeps them together? That's an electrostatic attraction, basically electromagnetism, attraction. One has electric charge, the electron has negative charge, the nucleus has a positive charge, so this produces an attraction. That's what makes atoms to be together, stable. They hold electrons to the nucleus. But the nucleus inside of the nucleus, if we have a nucleus of a helium, for instance, it has, say, 2 protons and about, say, 2 neutrons. Okay? A helium has 2 protons and 2 neutrons. Listen, these protons have a positive charge. It means that there is a huge force, a very huge force, that repulsion, positive charge of the same type, very close together because this nucleus is very small. So they should just split. This nucleus should explode away. There should be no nucleus at all, but that's not what happens. So something very strong is holding them together. You know? The electromagnetic force, electricity-based electromagnetic, keeps electron attached to the nucleus. Okay, that's electromagnetic. But inside of the nucleus is not electromagnetic, it's not electrical, it's not the Coulomb's law. The Coulomb law would make them explode. So there is something that bound them together. And there's something we call a strong nuclear force, not very creative. So there's something that's very strong. It's different from electromagnetic. This is a strong force. And then we have that beta decay. Remember that I mentioned at the very beginning when the first idea about the neutrino came into existence? Well, that process is not based on electromagnetic. It's not based on this strong force here. It's based in what? Well, this other thing we call weak force. Okay? It's a weak force. And it's very important for us this because neutrinos, as you're going to see, neutrinos perceive this interaction, the weak interaction. Neutrinos do not perceive the electromagnetic interaction. So if you may have a very strong electric field, neutrino will ignore that electric field, does not see, does not perceive, nothing happens to them. Even this very strong interaction that keeps the nucleus together, very, very strong, because it does not allow the protons to explode, to go away. Neutrino will get there, we see nothing. It does not perceive. So neutrinos only perceive something that's we call weak interaction. So then basically at the very end, we have electrons, we have protons, we have neutrons, and you have the neutrino. And in principle, electron, proton, neutron, and the electron neutrino would be enough for the universe. Everything around us is this. But unfortunately, there is much more than that. I mean, there is just to be complete, there is gravitation. So what keeps the moon attached to Earth in orbit is neither electric, nor this strong, let alone this weak one. It's something else, that's gravity. Gravity is not a subject of particle physics, because although a particle like an electron has mass, and proton also has mass, so they are subjected to gravity, it's too small compared to the others to be relevant to us. The only reason why you perceive here because the Earth is huge. So it has lots and lots and lots of protons, lots and lots and lots of electrons. All this together makes, no matter how weak that force could be, since we have zillions and zillions of them, is strong. So, but we don't take this into consideration, okay? Now, so briefly, we can see more of the particles if we have more energy. So here you have an atom. Then to see inside of the atom, you need to go into the nucleus. So you need more and more energy, like to penetrate. Like it's an analogy with a microscope, okay, or a telescope. You need a more powerful telescope and more powerful microscope to see more and more. It's smaller and smaller the thing are there. In that case, to get into if I try to get into the atom with a very small energy, I can't. Now, whatever I try to do, so I need more and more. And that's why our detectors and our oscillators suffer. But I'm not going to say that. But what's important to us is to understand that protons and neutrons are bounded states of quarks. So a proton, in fact, has 3 quarks: a quark, and a quark. We're going to talk a little bit about that. Okay. In fact, the proton has 2 quarks of kind U and 1 of quark D, and the neutron, the other one. So they are not fundamental. These quarks are fundamental. Okay? I'm going very fast through all this, okay? And then you have the first generation, the second generation, the third generation. What is this about? Well, as I mentioned, electron, proton, neutron, and electron neutrino would be enough. Okay? It would be enough. We'll be very happy with them. However, as I mentioned before, people found muons. And the muon is like an electron, but heavier. And together with the muon, they found the muon neutrino. And then later, they found the tau. That's pretty much like an electron and the muon, but even much, much heavier. And together with them, we have the tau neutrino. And the same happens for the protons. The protons, as we see, they are not fundamental. They have these quarks here, the U and the quark. So in principle, we would be also happy with the quark U and the quark D. But later, we found more and more. So what happens that there are 3 generations that, as if the fundamental particles came in groups, in families. The first generation, then there is the second generation. It's exactly like the previous one, but much heavier. And then you have the third generation, exactly like the first one or the second one, but even much heavier. And as I mentioned, the tendency is for them to go to decay to the one that's lighter. So the second generation eventually decay to become the first generation, the third to the second generation, then to the first generation. is there a fourth generation? As far as we know, 3. There are only 3. Please don't ask me why. Whoever designed the universe, that's how he did. But we can never be sure. But so far, as far as we know, there are 3 generations. So 3 repetitions of the same thing. So, and the electron, mu, and neutron are identical except for the mass. This is wrong. Here's is tau, okay? Okay. And we have evidence, very strong evidence, that there are only 3 generations. Yeah? So the universe has 12 fundamental particles. The electron, we see that. So we have the electron, the muon, we have the tau, we have the neutrinos, 3 neutrinos, and we have the tau neutrino, and we have the other quark, the quark U, the quark D, S, C, B, and the top quark. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's all. In principle, the universe, everything in the universe that's matter, I'm not talking about energy, is made of these 12 things. If you understand this, we can understand the whole universe. The very preposterous, but anyway, that's how. And again, we could be happy only with the first generation. That would be the first generation would be this one here, U and D, and the electron. But that's not how things work. Yeah? Just to have an idea, this gives an idea of the size of the size here is not the geometrical size of the particles. Okay, it's just to have an idea of their intensity. So here's the first generation, the second generation, the third generation. See, they get more and more. They get heavier and heavier and heavier. So the muon is heavier than the electron, and then the tau is heavier than the muon. The S here. You go to the second generation, and then you have D, the quark D, quark S, and quark D. P, and then you have the U, the C, and the T. So they are pretty much like the same. U, C, and T are pretty much the same, but the T is much heavier than U, and C much heavier than U. This is, and it's a little bit strange because why there's so big difference in mass? How did it happen? Okay, some theories try to explain that. And here we have the neutrinos. So a question is, remember that I mentioned before the mass hierarchy. If this follows the same pattern, then this muon neutrino would be a little bit heavier than the electron neutrino, and then the tau neutrino would be heavier. This is still to be checked, decided. Okay, if it's not, it would be very strange, but that's anyway. Okay, and something interesting to note here is the following: the electron, the muon, and the tau, they have electric charge of -1. Okay, but when you go to quarks, a big surprise happens. The quarks, the electric charge is not an integer; it's -1/3 or +2/3. And you see here you have, see the U. These 3 have a charge of -1, and these other 3, the 2/3. Okay, they may look like the same, but their mass is very different. See the U and D, the quark U and the quark D, the mass is pretty much the same, very close to each other. But then we go to the next family, the second generation. Oh, it's much bigger. This is almost 1,000 times bigger. Okay? 0.003, and here you have 0.1. It's 300 times bigger. And go to his one. See, the last one, the top, is ridiculous. It's huge. This is strange, right? But anyway, that's how it is. Okay, but how do they interact? And something I want to say is this is a quote from Isaac Newton in 1693. Okay. Newton was concerned with something. Newton made all his theory. Is considered a genius. And basically, what you know is that if you have two pieces of matter, M1 and M2, you have here M1 block, that's M1. And here you have another one, another mass, M2. Okay? Then we know there is an attraction, a force. And we have the expression of the force is G, M1, M2, divided by the square of the distance of them. Okay? That happens with the moon and the earth. Okay? Or if we have two tomatoes on the table, there's an attraction between them. The tomatoes do not move to each other because this force is too weak, because tomatoes are too small, and they stay on the table. But what bothers Newton was the following: how come? How could that happen? He could not understand. It's inconceivable that matter, should, without, there is nothing. There is nothing between the moon and the earth. Empty space, for instance. How can they attract each other? In a very simple terms, okay, how does the moon know about earth and earth about the moon? So they do not touch each other. If the two things are touching, it's easy. Okay, you get with your hands, you go and get an apple on the table. Okay, you are touching. You can understand. But in that case, there is no contact between the earth and moon. How do they interact? There's a force, but how come? What's mediating that interaction? Newton did not know that. He was confused. He was uncomfortable with that. He makes it very clear here. He does not understand. And I believe, at the end, he said, I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Because he did not accept that very well, but that was the reality. And you have to do the same thing now. We have two particles, two electrons. From Coulomb's law, we know from Coulomb. You have the force, will be, now we call K. Here we call K, here we call G, big deal. Okay? Then it will be the charge of one particle, the charge of the other particle, and again, the same. Okay? It's the same expression, the same thing. Okay? How it happens? How the two charges interact? To interact, something must be exchanged. That's our idea. Someone speaks, the other one can understand. I should have finishing about 5 minutes or so. I should have finished. How did it happen? So how that could happen? Well, the idea we have is that something is exchanged. Okay? If we have two electrons, there is a force between the two electrons. The way they know about each other is that they exchange something. Like one, here, send a signal, let's say like that, and that the other captures that signal, and so they interact. They can respond. If someone sends a signal and the other one cannot capture that signal, nothing happens. Okay? So that's how we represent here. This is just a representation of things here. I'm doing it here with electron, but it doesn't really matter. So here we have one electron. Okay? And then here I have another electron. What happens that one of the electrons, for instance, the first one, sends something that's a photon. Sends a photon. And the other one captures that photon. A photon. Receiving a photon. Something. And so, the same happens the other way around. The second electron may send a photon. So they are both sending photons and receiving. So if they send a photon and the other one receives, they exchange something. Is this exchange of this something is where to make they interact. In the case of the photon, in the case of the electron, the results is that they will repel each other because they have the same charge. But if it's an electron and a proton, they have different charge, the result will be that they will attract each other. So they exchange something. So the reason why the electron is attached bound to the nucleus is because the electron that's negative and the proton, the nucleus that's positive, they exchange photons. And when they receive the photon for each other, they react. That reaction produces the attachment. But for that, they need the electric charge. And inside of the nucleus, why the protons stay together despite of the electric charge? Well, they have electric charge, so they are also exchanging the same photon. That's to make the electric interact, the Coulomb force. But they also exchange the same other thing that we call a gluon. These other things, electrons cannot exchange gluons. They don't have whatever produces gluon. But protons and neutrons have gluons, so they exchange gluon, and by exchange, the same similar effect happens. Okay? And with the similar effect is such that keeps them together. So two things are happening there. The protons are exchanging the photons, so they are interacting electromagnetically, and for them to interact, they should explode the go, right? But they also exchange these gluons, and when they exchange gluons, yeah. And what about what we call weak interaction that makes the beta decay? It's not electromagnetic. What's exchanged, what's involved there is not a photon, and it's not a gluon. It's something that we call a W and a Z. And we are going to talk about this because that's what happens with neutrinos. Neutrinos have no electric charge, so a neutrino is blind to photons. So an electron may be close to a neutrino does not see anything because it cannot collect photons. Proton may be close to a neutrino, and there are gluons there, but the neutrino does not see gluons. It's blind to gluons, so nothing happens. But neutrinos are not blind to these two things here, the W and Z. So we're going to see how that works and understand a little bit how interaction of the particles and neutrinos happen. I hope to finish this tomorrow. So it'll be important for us to understand some features of the neutrinos. Okay? I'm going to stop now because it's already 1.5 hours. Now it's 4:30 my time. It's what time? 2:30. 2:30. Yeah. Okay? So we finish tomorrow. There are lots of things to say, but I will concentrate basically in this week. That's the force that affects neutrinos.
Okay, Hélio, thank you. Well,
tomorrow the same time, same channel.
Okay, yes. I want to thank Professor Hélio Motta for today's lecture, and we will resume tomorrow at the same time, 1 p.m. Okay, Hélio, thank you very much. See you tomorrow, guys. Good afternoon to everyone.